Hello, welcome to Peterson Rocket Propulsion Laboratories, or P.R.P.L. In today's video, we are going to be taking a look at nozzle theory and isentropic flow. There are two main types of nozzles, converging only nozzles and converging diverging nozzles, also called CD nozzles or de Laval nozzles. This video will mainly cover the fluid dynamics of the de Laval nozzle. First off, what is isentropic flow? Isentropic flow is fluid flow through a system that is frictionless, meaning it's reversible, and adiabatic, meaning that no heat is lost to the surrounding area. In nozzles, isentropic flow is desirable and is determined by changing cross-sectional area. The whole point of a nozzle is to accelerate combustion gases to supersonic speeds at the exit, meaning the Mach number increases along the nozzle. This in turn causes higher thrust to be produced, which is ideal to make a rocket go higher. Nozzles need certain things to happen in order for it to function. They need constant flow, the mass flow rate needs to be constant, they need to be one-dimensional, and they need to be with a compressible fluid. Compressible fluids allow for density to change and therefore allows for velocity to increase, unlike in incompressible fluids, such as water or any liquid. We can see the characteristics of a nozzle in this diagram. As we can see, it is one-dimensional. It flows from the combustion chamber to the exit of the nozzle. We can also see that the mass flow rate is constant, and it has a changing cross-sectional area. This changing cross-sectional area causes the velocity to change along any point x in the nozzle. As we can see, it starts off at a subsonic speed, the Mach is less than 1 here, and then it converges to the throat where it is at transonic and supersonic speeds. Then, towards the exit, it expands, and that is where we see the increase in velocity. All nozzles accelerate combustion gases simply by changing cross-sectional area. We can see that here in this diagram. Why is the cross-sectional area changed? Well, it's based off mass flow. Mass must be conserved throughout the nozzle. Because of this, as the area gets smaller, the fluid has to increase speed in order to keep a constant flow rate. This is only the case at subsonic flow. We'll talk about supersonic flow in a second. It's pretty weird. The smallest area in a nozzle is called the throat, right here where the red marker is, and is ideally the critical spot where the fluid velocity is Mach 1. This is called choke flow and is most efficient for a rocket nozzle. Any further decrease in area will actually result in the slowing of the fluid. The throat is critical while designing a nozzle, and is what expansion ratio is based off of, and is where flow reaches supersonic speeds. The decrease in area from the combustion chamber to the nozzle is called the converging section. Now here's where things take a weird turn. Because of the interesting physics of supersonic flow, in order to further increase the fluid velocity, the cross-sectional area actually has to expand from the throat. We can see that here with those green lines. This is because the rapid changes in density from the fluid causes the velocity to continue to increase. I'll explain this more in depth a little later. Think of it as there is more room for the gas to expand and pick up speed. This increase in area after the throat is called the diverging section of the nozzle. Now that we know how a nozzle functions, we can use the properties of isentropic flow and the isentropic flow equations to govern and visualize the relationships of temperature, pressure, density, area change, and exit velocity in the nozzle. First up is temperature. This equation relates the temperature along the nozzle to the stagnation temperature, or chamber temperature. Gamma, this little y right here, is the ratio of specific heats and is different depending on the gas. For air, it is just 1.4, and that is the constant that I used in this graph. M is the Mach number of the gas. As combustion gases continue through the nozzle, the temperature decreases greatly. We can see this by this graph. It first starts off and decreases as the Mach number goes up. Next is pressure. This equation is used to relate pressure along the nozzle to the chamber pressure. The same constants are used as in the equation for temperature. As we can see, as the Mach number continues to increase and we continue along the nozzle, the pressure decreases greatly. It is very steep, as we can see in this graph, compared to the temperature one. This then expands correctly to ambient pressure, that is generally most efficient and is correctly expanded. The pressure drop is also because of the effects of the Bernoulli's principle. It states that a fast-moving fluid will have a lower pressure than a slow-moving fluid. So since the fluid keeps on accelerating, the pressure keeps dropping. Last is density. Density is important as it is what drives the divergent section of the nozzle and increases the velocity. This equation gives the relationship between the pressure along the nozzle to the gas density in the combustion chamber. As we've seen with the other gas characteristics, the density of the gas decreases as we continue down the nozzle. This is important to increase the exit velocity. This graph is extremely similar to the pressure one, as the only difference is instead of 1.4, the gamma value, it is just 1, so very similar. This equation relates the ratio of pressure, temperature, and density all to one another. Each of the characteristics are super important, and we can see that they are all very closely related. Now, it is important to know that each part of the equation must be analyzed at the same part of the nozzle. For example, the pressure ratio and Mach number must be taken from the same cross-sectional area in order to keep the function true. In the example of this diagram, we need to take all the values, say from this point, or at the exit, or at the throat. You can't take different variables from different sections of the nozzle. Next up, we are analyzing the area change in the nozzle. This equation relates the area along the nozzle to the throat area, based on the Mach number. This graph shows what happens to the area ratio as the combustion gases continue to accelerate. What we see is that as we start to get past Mach 1 and into supersonic regimes, is that the ratio of the area to the throat increases, given by this spike here. It is equal to 1 at the throat, obviously. The faster you go, the more you expand. Depending on your pressure, temperature, velocity, there will be an optimum expansion ratio to have the ideal expansion to achieve max performance. You don't want to be overexpanded or underexpanded. The optimum expansion ratio is given by the area at the exit over the area at the throat. Lastly, I want to talk about exit velocity. The exit velocity is very important, as the nozzle aims to achieve the highest exit velocity possible. These two equations tell you how you can find your exit velocity. Exit velocity is impacted by the temperature and pressure of the gas greatly. As seen in the first equation, the exit velocity is directly proportional to the square root of the temperature. We can see that right here, with the temperature of the exit greatly impacting the velocity of the exit. A higher temperature means the rocket will start with more energy, and therefore the exit velocity will be higher. This explains why a cold gas thruster will always have a slower exit velocity compared to a conventional, high temperature rocket, such as the Falcon 9 rocket. Exit velocity is so important as it increases thrust. In the thrust equation given here, we can see that it is largely based off Newton's third law of motion. The second term can largely be ignored, as ideally the exit pressure and the ambient pressure are the same, so the term equals 0. Therefore, we can see that a higher mass flow rate and a higher exit velocity will increase our thrust, which is why nozzles try to increase velocity so much. Now, I said earlier that the continual decrease in gas density is what drives the diverging section of the nozzle and the exit velocity. While this is true, the real physical mechanism that drives this inverse relationship of gas acceleration from the area expansion is a little out of the scope of this video. But to clear up, we can use mathematical restraints to see how mass flow conservation explains why velocity increases. As we know, the mass flow rate of the nozzle stays constant. Given by this equation, we can see that mass flow is directly proportional to density, area, and velocity. Given the weird properties of supersonic flow and mass conservation, the rapid decrease in density causes the velocity and area to increase to keep the mass flow rate constant. So, as the density lowers, in order to keep this the same throughout the nozzle, the area and the velocity must increase. That's why we see this bell shape or this expansion from the throat. Well, that pretty much sums up my video on nozzle theory and isentropic flow. I hope that these confusing topics made at least a little more sense. And of course, if you find any mistakes in my video, please feel free to tell me in the comments. I have left my sources and references down in the description, and if you have questions, feel free to look at those. Thanks for watching.